Hi there. Today we'll look at Hopfield Networks is All You Need by researchers from the Johannes Kepler University in Linz and the University of Oslo. So on a high level, this paper proposes a new type of Hopfield networks that generalizes modern Hopfield networks from binary patterns to continuous patterns, and then shows that the retrieval update rule of these new Hopfield networks is equivalent to the attention mechanism that's used in modern transformers. And it's actually a more general formulation of the attention mechanism, and therefore it can be used to do kind of a variety of things to improve modern deep learning. And it also has a companion paper where it applies this to some kind of immunology research and achieves state-of-the-art in a task that is specifically suited to this type of attention. All right, let's dive in together. We'll go over what this paper does, what it proposes, and so on. If you like videos like this, consider subscribing, sharing it out, and I hope you're enjoying this. All right. Also, thanks to my Discord community for very helpful bringing me up to speed on this paper. Super interesting discussions there. If you're not on our Discord yet, I invite you to join. It's fun. Okay, so what is a Hopfield network? A Hopfield network is a pretty kind of old conceptualization of a neural network. So in a Hopfield network, what your goal would be is you can conceptualize it as a bit of a neural network. So let's say we have 5 neurons or something like this. What your goal would be is to have a neural network where you can store so-called patterns. And a pattern in this case would be a binary string of size 5. So for example, 1 0 1 0 0 or 1 1 0 1 0. And you'd have a list of these patterns. And what your goal would be is to store these patterns in the neural network such that, and here, we'll just consider everything to be sort of connected to everything else. And what your goal would be in this is that you can kind of store patterns inside this neural network and you adjust the weights somehow. So this was, as I said, this is kind of an old model. You adapt the weights such that you store these patterns. And what does it mean for a pattern to be stored? If you have stored a pattern, you will then be able to retrieve it. And you retrieve a pattern in these kind of old style Hopfield networks by providing a partial pattern. So what you'll say is, for example, I want a pattern that starts with 1 1 0. And you give that to the network, and there would be a so-called update rule. And the update rule is kind of an internal rule. So let's just go through this. So here, this 1 1 0, maybe this is 1 1 0, and then they would kind of send messages around. So this update rule would somehow adjust the value of this and this neuron here to what's most compatible with the network weights. And if the network weights have been adjusted correctly, this will turn out then at the end of applying this update rule that this is a 1 and this is a 0, and therefore this pattern here is retrieved. Now, had I input 1 0 1 at the beginning, then the outcome would be different. Hopefully this pattern here would have been retrieved. Okay, so you can see the applications of this, like you can have the first 3 digits as sort of a database key, and then the last ones as sort of the value that you store along with it, and then you can simply provide the first few. You can also provide, you don't always have to provide 3. So this all depends. This is sort of as I said, an old conceptualization of neural networks. So people were imagining that this is kind of how the brain works, fire together, wire together. And also with research into this, it turns out that, you might think, there's kind of 5 neurons. So maybe I can store 5 different patterns, accurately. Because if I store too many patterns, right, if I have many patterns, then I can't expect to be able to retrieve all the patterns again, because some of them will just be so equal that, you know, many will start maybe with this, and I won't have a chance to retrieve the one I want, or the update rule will make a mistake. So you might think this might be like 5 because I have 5 neurons, or maybe 10 because I have 10 connections, but it turns out that in modern Hopfield networks, with the appropriate update rule, you can store exponentially many patterns in these networks, exponentially many in the dimension of the patterns. And here, I guess that would be the length of the pattern. So this is a little bit surprising, the kind of storage capacity of these networks, and this paper here generalizes that to continuous states. So what do we mean with continuous states? I guess I mean continuous patterns. So no longer is a pattern a binary string, but a pattern now is a string of floating point numbers, okay, like 0.5, 1.3, and so on. And, you know, a string of floating, or a sequence of floating point numbers, is naturally depicted as a vector, okay? So our patterns are going to be different vectors that we store, and, you know, in high dimensions, that the vectors will be kind of separated well from each other as long as we don't have too many. But this paper shows that all these properties for the modern Hopfield networks that hold for binary strings still hold if you go to these kind of continuous, to these vector patterns. That means you can store exponentially many patterns in the dimensions of the vector, which is pretty surprising, right? Because you'd think, like, you know, after you have one vector per dimension, that, you know, after that it might get a bit shaky. But no, you can actually store exponentially many. So that's pretty surprising. And this paper is a lot about how to do that, the fact that that happens, and so on. So we've talked about update rules for these kind of Hopfield networks, and I haven't really specified what that is. I've just said that, you know, I enter a pattern, and then the network does something, and out comes the whatever the pattern that matches my query. So this here is called a query. You might already, this is on purpose, like the kind of overlap between the attention mechanism lingo and the Hopfield network lingo. We're going to conflate the two to kind of make clear where the two overlap. If you don't know what an attention mechanism is or aren't familiar with it, watch my video on attention is all you need. Once you watch that, this video will make a lot more sense. All right, so in what the update rule does is, specifically, and the update rule, there isn't only one, right? There are many different proposals of Hopfield networks, and they all lead to different properties. But what an update rule does ultimately is it minimizes what's called an energy. So every type of Hopfield network is associated with an energy function. And the energy function of the modern Hopfield network for binary strings is this energy function right here. So with x is the pattern, this is the kind of state of the Hopfield network. And so these are the whatever is stored in the network. And then the xi here is the query that you enter into the network. And then the energy here tells you this quantity, you have to minimize this quantity in order to retrieve the pattern that you want. Okay. Now, we are never directly working with the energy as such. So what you could do is, for example, use backprop or something to use gradient descent to decrease the energy. But usually, along with an energy function comes an update function. And the update function is what I've talked about here. Like, you do something and then the network does something and then you get the pattern out. What the network does is it minimizes its energy function. and the update rule is made such that the corresponding energy function is minimized. So the energy function is more like a theoretical consideration that you say, okay, here is my energy function of my Hopfield network, and there will be a corresponding update rule that minimizes that energy function. And if you use that update rule maybe multiple times, then the energy function will be minimized and you will have retrieved your pattern. Or not. If you have too many patterns stored, it might also fail. Right? So they say what the update rules are in the text here for the old Hopfield networks, but we're not really interested in the old ones. We're interested in the ones that this paper cares about, namely where the patterns that you store in the Hopfield network are these vectors over our vector patterns, and the query is also a vector pattern. So you want to store all of these patterns into the Hopfield network. So I'm going to draw it like this here. You want to store it into the Hopfield network, and then after that you want to come up with a query, and the query is like this. And in the case of the binary strings, we had something like, well, I sort of know half of my binary string. Now in the vector Hopfield network, it's more like, well, I sort of kind of know the direction that my vector should point in, okay? And you will what you want to retrieve is the vector that has kind of a large inner product. Okay, so if I enter this query into my Hopfield network, what I hope is that this vector here is retrieved. Now you see, it's not exactly the same vector. Like they do point, if I translate that here by I, it's maybe something like this. But so they are different, but you want to say, well, I kind of know what I want. I kind of want something like this. And then the Hopfield network would answer with, I have something like this. It's this right here. Okay, so that the connection to attention mechanism should become pretty obvious right now. But you know, the to actually establish this formally is the kind of the point of this paper, and you know, it's pretty cool to see. So they formulate this new energy right here. This is the energy of this new continuous Hopfield network. Specifically, they have to have this term right here because they now have continuous states and continuous queries. If you minimize the energy, it basically means that your query can never, you know, go to infinity because you have the query right here in the energy function. The update rule is this right here, and we'll look at that in a moment. But remember, the update rule is what you actually implement in code. So if I have a query right here, I plug it in here. This is the state of my Hopfield network, and I apply this rule multiple times, and out comes the kind of answer of the Hopfield network to my question. So I input this and the out comes this after I apply the update rule maybe multiple times, right? And interestingly, you can already see that this here, if you rewrite a bunch of these quantities, so if you rewrite the beta here, which is the softmax temperature in a way, to be 1 over square root of d, and if you take the query, the xi here to be the query matrix, and if you take the x here to be the key matrix, then this is equivalent to the the attention mechanism of a modern transformer. So that's the point of the paper, is that we can look at the transformer attention mechanism as a Hopfield network. And they have this interesting diagram at the end right here. So the appendix, you know, this is typical, I guess, Sepp Hochreiter. I remember this Celu paper had like 60 pages of machine-proof appendix. This has like 70-page appendix. Crazy. But at the end of the appendix, you'll find this diagram right here. Now, usually in an attention mechanism, you have whatever the input is. So you have an input right here. So this is attention mechanisms, or at least transformers, they work on sequences or sets of objects. And from these, you'll generate three things. You'll generate the queries, the keys, and the values. Now, you can either generate the queries from the same objects, which would be self-attention, or you can generate the queries from like a different object over here. It doesn't matter too much for our discussions, but either you have a reference input, or you have this kind of same input all the way. And then what you do is you use three different heads, or three different matrices, to transform that input into queries, keys, and values. So I often conceptualize this as you have kind of your input set, and each of the input sets outputs a key, and also each one, which would be a vector, and also each one outputs a query. So I often draw this here, the same sequence, and each one outputs a query. And the query is kind of a request for information. So the key exposes exposes something about the input here. So this could be a sentence down here. This could be, my cat is very pretty. And the vector, the key vector right here, could encode something like, this is a noun, or this is an animal, or anything like this, right? And the query here, it could ask for other things. So for example, since this is cat, this vector right here, the query vector, is generated from that token cat. Now, it could recognize that cat is a noun, and it could ask the other nodes to basically say, are there any adjectives around here? Because adjectives, because it itself is a noun, it's the object of the sentence, right? It could ask, are there any kind of adjectives that describe the object? Because that would be naturally a thing to ask. If you were the noun, you would want to know, are there any kind of modifiers for me? So it could output the query, and the query here could mean, this direction could mean adjectives. And you see here, the word pretty is an adjective. So it itself would output a key that says, by the way, I'm an adjective, right? So if the cat asks, then if this node asks for an adjective, and this outputs the adjective vector, then because the inner product between the two things is high, this will be routed here. So attention mechanism is basically information routing. That's how I always describe it. But in this paper, we look at it more like, these here are the patterns that are stored in a Hopfield network. And by inputting a query, and the dot product being the update rule of the Hopfield network, I retrieve from the Hopfield network, I retrieve the appropriate pattern that I ask for, okay? And then, the values are simply a modification of the keys in this form, but a lot of people also do keys and values to be the same thing. But this routing of information happens here, where you multiply the queries and the keys, and then you put a softmax over them, okay? So if you just look from the perspective of a single node, like this node here, this cat node, what it would do is it would inner product its own query vector with all of the key vectors, right? So it would build an inner product with all of these, and then it would normalize. It would put it through a softmax, which will kind of give it a distribution, right? So here would give it like, so this actually matches, because my is also very important for cat. This is just an accident. I did not plan this. This here, this also, many things match, but in our example, we would just say that this last one, it's not only higher, it's also wider. It matches very well, right? And so the information routing would route mostly information from this pretty token to the cat token, which makes sense in our case, right? This is the attention mechanism. Now, if we are interpreting this as a Hopfield network, and the update rule here is the dot product, you can actually think of applying this rule multiple times. So what happens now if we, and this is where this update rule comes in. What happens if we take this distribution and we don't aggregate the values? Like usually we would aggregate the values by this distribution. What if we aggregate the keys by this distribution? Okay, what comes out? Well, if we look at this, and let's just assume that this key right here matches really well, but the others also match a little bit. What would come out would be a weighted average where a lot of weight is put on this particular key. Right? So what will turn out would be something that's very close to that key. You can see I'm going to draw the old key here in green, and I'm going to draw the old query in blue. So you see that whatever comes out is not the query, but it's also not that only key that matches, right? It's kind of a weighted average, but with that key dominating. Okay. Now, since, in a Hopfield network, what we would do is we would go again. We would put this new thing, the red thing, instead of the query vector. Okay. So we would use this aggregated keys, this weighted average, as a new query vector for that node right here. So I'll duplicate that node over here. I'll use that query vector again and do the same thing again, okay? Inner product with all of the query vectors. And now, since this is already an aggregate of the query vectors, what's going to happen? Of course, the distribution that's going to come out is going to be weighted even more heavily into the direction. So let's make it even wider. Into the direction of that key that matches, okay? And you can pretty clearly see if I do that iteratively, then that will lead to a situation where everything is like very low, except that one key will sort of dominate the distribution, and ultra high and ultra wide. Okay, and that's exactly how a Hopfield network works, right? I would input the query, which would be sort of what I want, right? I kind of know what I want, okay? And then I apply this rule multiple times, right? And with each time, I refine until I decide on a pattern, right? The Hopfield network is made for pattern retrieval, and these here are the patterns that I want to retrieve. So here, the patterns aren't kind of stored in the network beforehand, but the patterns are also generated like in an attention layer. So the keys are generated by the previous layer or by these matrices, but that doesn't matter for the Hopfield network update rule. So you see here that the attention mechanism can be interpreted as simply one step, making one step of this update rule, but you can think of making actually multiple steps and retrieving the particular key. So deciding on a sort of a hard routing of particular information. Now that only works if there are no other vectors that are close to that particular key, right? So if the query is this, and the way I drew it here, you can see that there are many. There is this one and this one and this one that matches. So technically the way I drew it, what would happen most likely is no matter how many times you apply your update rule, it would sort of result in kind of the average of the three keys, right? So because they're all matching and they would all contribute to that weighted average of the query in the next step, and then that means basically the convergence would be to something in the middle. And that's going to be a central point of this paper, in which situation we are. So they call the first part is retrieving a single pattern, and they call the second situation where you have multiple patterns that all match, that are not well separated from each other. They call this a meta-stable state, and it's going to be pretty interesting to look at like BERT language models and look at where they actually are. Are they actually operating in this single pattern retrieval mode, or are they operating in the meta-stable state mode? All right, so here you can see it in the diagram. The only thing differing this from a Hopfield network, from an attention mechanism, is this branch right here. So here you ask, do you want to do multiple updates? After you've multiplied the queries and the keys, do you want to do multiple updates? If yes, so if you're in this Hopfield network situation, you want to do multiple updates, then you go back, as you can see, and you use the keys together with the output of the softmax to generate a new query. So this query queue here is now generated from the output here and the keys. So the keys are the same. This is the same thing. It's just put here twice. Okay, this is exactly what we discussed. Okay, I hope that's somehow clear that the attention mechanism is simply a one-step Hopfield network pattern retrieval algorithm with a particular update rule that matches this energy function that they propose right here. Of course, they do this, particularly because the update rule that turns out is the transformer update rule. But I actually don't know if they backwards engineered the energy function to match the transformer, or if they first came up with a continuous Hopfield networks and then kind of discovered that it's like the transformer. We'll maybe never find out. Okay, so let's go. There are a couple of theorems. I believe there are 5 theorems right here that that kind of make some points about this stuff, and we'll go through them. We won't go through the proofs or any super in-depth meaning, but it's pretty cool to go through them, and they are proved very rigorously. As I said, there's a 70-page appendix, so have a look at that if you're up for it. Okay, so they say here we have an update rule. This is our update rule for our new Hopfield networks. So the first theorem they say is the update rule that we propose converges globally. If we apply the update rule repeatedly, the energy for t equals infinity, and the energy will converge, the energy will converge to a fixed point, this being a fixed point, for t equals, for t goes to infinity, if this is a fixed point. Basically saying that if I apply this update rule here over and over and over again, it will make this energy function converge to a fixed, it will make this energy function converge. Don't want to say anything mistakenly here or claim too much, but that basically connects the update rule to the energy. Okay, so just showing like this really is the update rule for that particular energy function. Okay, now as itself, it's not super duper interesting yet, but now we get to theorem 2. So theorem 2, for the iteration, that's the update rule that we just looked at. We have that this convergence holds as t goes to infinity for some stationary point. Furthermore, this quantity here goes to 0. So that means this is the update at t plus 1, and this is the update at t, and the difference between them goes to 0. So that means not only does the energy converge, but the iterates themselves converge. So the algorithm actually converges. The individual updates of the algorithm, so this E new, at some point that will no longer change because the norm between it and the previous one will go to 0. You can see that either the sequence here converges, or in the other case, the set of limit points, yada, 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 is a connecting subset. This is a bit over the top here. They say, Okay, it can either converge to a point or it can converge to a connected subset. But if the loss is finite, then any sequence generated by the iteration equation 3 converges to some fixed point. So, basically saying that here oh, this is not the loss. I'm sorry. No, this is the domain. Never mind, I'm an idiot. This is basically saying that this algorithm will converge, okay? And they define here what it means for a pattern to be stored and retrieved, and that's for establishing what the kind of storage capacity of a Hopfield network is. So we've established that the update rule minimizes the appropriate energy, and the update rule will converge at some point, which means that we can, if it converges, we can retrieve the pattern that it converges to. So now we define how many patterns can we actually store. For that, we need to know what does it mean for a pattern to be stored. So we assume that we have patterns, and these patterns are called X. Okay, Xi, we have n different patterns. Each one is called X with a subscript. We assume that around every pattern, a sphere is given. So how do we imagine this? We have these patterns, and this is just a space. Now they consider patterns of the on a sphere, but we'll just conceptualize it as this. We'll have a space, and there are patterns we want to store. Okay, and we'll say around every pattern there is a sphere. Okay, sphere like this, and naturally the patterns are going to be, there's going to be a notion of well-separated patterns, and you can imagine this a little bit like these spheres won't be touching each other. If these spheres aren't touching each other, that means that the patterns are kind of well separated. And that means that if we initialize the query, remember the query here is a vector that kind of sort of looks like a pattern, and that means the query is kind of close to the pattern in some notion of distance. So if we initialize the query somewhere in that sphere, then it might, if it converges to that sphere, to that pattern, then we retrieve the pattern. Okay. Now it gets a bit more complicated than this, but not much more. So we say a pattern is stored if there is a single fixed point inside the sphere to which all points that start inside the sphere converge, and none of the spheres intersect. So the sphere of point I doesn't intersect with the sphere of point J. So that's where we say all these spheres are non-intersecting. We say Xi is retrieved if the iteration equation 3 converged to the single fixed point in that sphere. The retrieval error is the distance. So you'll notice you have two things. You have Xi, this is the actual pattern, and you have Xi star. This is the retrieved pattern. So these Hopfield, they don't always have to give you the same thing that you stored. That's part of the nature of continuous neural networks, whatnot. So for every sphere, we say there is a pattern, there is a sphere. Now, as pattern is stored, if I can start wherever I want in this sphere, okay, wherever I want, it will always converge to a point that's inside the sphere. Okay. And maybe that point isn't the pattern that I stored, but actually this point right here. But wherever I start, I will always converge to that particular point. If that's the case, then I have stored this particular pattern. Now, the fact is I don't retrieve this particular pattern, I retrieve the blue thing, but I can then define the error of retrieval, and the error of retrieval is simply the distance between the two things. Ideally, this distance is very small, right? But we can't guarantee it. Now, there are going to be theorems that deal exactly with this retrieval error. But first, you can see that here, if these spheres become larger, you can't accurately store a pattern anymore. So this is the kind of ideal situation, but there are also situations where these spheres, if I have these patterns right here, these spheres are so large, kind of the attractions of the patterns are so large that if I start, let's say here, then I don't converge to either of these two patterns. I converge to like something in the middle. I converge to maybe this point right here. And that's going to be one of these meta-stable states, okay? We're going to encounter situations like this, but we're also going to encounter situations like this. And the bottom thing isn't necessarily bad, and that's what you have to keep in mind. And yeah, as I said, we'll get to it, but just keep this kind of sphere image in mind, okay? So first, we'll just deal with the, the top situation where we store patterns and then retrieve patterns. So we'll assume a failure probability, which is P, and P is going to be, pretty low for their example. So they have P equals 0.001, like a 0.1% error probability of retrieving your pattern, things like this. And randomly chosen patterns on the sphere with radius m. We define some constants, yada, yada, yada. Then with probability 1 minus p, the number of random patterns that can be stored, and stored in the sense of having these spheres around them so that you can retrieve them accurately, or at least you can retrieve something that's close to them, is lower bounded by this quantity right here. So there's the square root of p, there is this constant c, but then you see that d is in the exponent right here. So that means it's exponential in the number of dimensions. So that's pretty cool. So if you add a dimension, you exponentially increase the number of patterns you can store. And that is a kind of, it's been known for modern Hopfield networks with binary strings, so it's not uber surprising, but if you have, it's not what you would imagine, like that. Okay, so they may give a few examples of these. You have to set these constants, in a particular fashion such that this is given and so on. But they say, examples here are where C is something like 3 and D is 20. So if you were to add a 21st dimension, then your, storage capacity would increase by a factor of 3, which pretty cool. All right, so this is how many that we can store exponentially many patterns in these networks. Now, they say, the next theorem states that the update rule typically converges after one update if the patterns are well separated. Okay? So if we're in a situation where these patterns are well separated, which is kind of like this, but you can also imagine this in terms of dot products because we operate in the space of dot products. So if the patterns are well separated, that sort of means that they all kind of sort of point away from each other. And this notion of separation is going to be captured by this quantity right here. This is the separation of example of pattern I, which is just the inner product with itself minus the maximum inner product with any other pattern. And this quantity is going to be large when no other pattern is close to it. So when the separation is large, then the update rule, the retrieval rule of calculating, I have a query, calculate the inner product with all of those, then I reweigh all of the patterns by that inner product, by the softmax, then I use that new thing as a query again and so on. As we discussed, it will converge to the closest pattern. But this theorem says it actually converges pretty fast. And here I have my problems with saying that it converges after one step. Typically converges after one update, because that, genuinely depends on a lot of constants, as we'll see, but it does converge exponentially fast in this separation constant. And so theorem 4 says, with query xi, after one update, the distance of the new point to the fixed point is exponentially small in the separation delta I. The precise bound using the Jacobian and its value in the mean value theorem are the following. So here you can see this is the distance between the updated xi after one step and the fixed point right here. This is what it converges to, is going to be the distance as it was before times this thing right here. So you can see, since this is a multiplicative update, and in this Jacobian, so this is expanded down here, this is this, you can see here you have this, sorry, yeah, this is this, so this is bounded by that. You have the exponent, the exponential function, negative this separation right here. So the higher the separation, the faster this algorithm converges, okay? To say that it converges after one step is, you know, it might be a bit of bragging. I don't know if this is a common thing, if you have like an exponential convergence that you are allowed to say it's after one step. I'm not sure. Especially what I'm not sure about is that you have n here as linear constants in that factor. Okay, so if you, and that's what they do in their code. So if you look at their code, and the code's available, which is pretty cool, it's implemented in PyTorch as a general module that you can just drop in. So this is not only for transformers, this is for, you can replace like LSTMs, you can replace pooling mechanisms, you can, you know, do a whole bunch of stuff. In their paper, in their accompanying paper, they do this multi-instance learning with giant sets on using these Hopfield layers. So pretty cool. This code is definitely worth kind of checking out, and maybe you want to replace some stuff with you. But the question is, how many of these update steps should you do, right? Because we looked at the diagram, at least in the attention mechanism, it seems like you have attention layers, right? You have a transformer, and the transformer consists of, you have this input right here, and you go through layer, 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 layer. And in each layer, there's contained in it one of these attention mechanism, right? This entire thing is in this layer, okay? And now if you interpret this as a Hopfield network and you want to do multiple steps, that means you go this branch right here. So in each layer, potentially, you do multiple steps of these things. So, you know, for whatever computational constraints transformers had already, this will certainly make it worse. But also you need to decide how many steps you want to do. Now you can hard code that, of course, but they say you should do these steps until this norm here, until the norm between the old and the new is small enough. So where is that? So you can't measure how close you are to the convergence points, right? Because you don't know in practice. But you can measure how far you're away. You can measure, where did we have it? You can measure this quantity right here. That's something you can measure, how far two iterates are apart. So what you'll simply do is you'll measure that, and if that is small enough, then you'll stop. But that, I guess, is very related to this. So how, we've already proven it converges to this X star. So I guess we can approximate this quantity right here with the quantity above. And that tells you how many updates you need to do. And that quantity is linear, not only linear, but actually here quadratic in n. I don't care, you know, yes, it's exponential in the separation, but it's quadratic in n. And if I've learned anything from kind of my fast code courses, is that constants actually matter when you're not dealing with infinity, with an infinite number of steps. So the number of steps you need to do, I guess, will depend on the sequence length in a quadratic fashion. So I'm not sure you can always claim this is converges in one step. Now I might be super mistaken here, and none of this actually makes a difference in the light of the exponential decay here. But I'm just a bit worried saying this usually converges in one step. It's clear, I guess, why they do it, right? Because the attention mechanism in transformers is a one-step application of this rule. And this here is kind of a theoretical justification for interpreting this precisely as a Hopfield network, because you'd say, well, in a Hopfield network you would do multiple steps, but wait, we can actually prove that even if you interpret it as a Hopfield network, it usually converges after one step. So what you're actually doing in a transformer is applying a Hopfield network update rule to convergence. So yeah, I might be bickering on a high level here, luxury problems. Theorem 5 then says, so theorem 4 is how fast does this converge? Theorem 5, the last theorem right here, says that the retrieval error of a pattern, then so this is what you converge to, and this is what you've stored, is bounded by, again, something that's exponential in the separation right here, as you can see. Okay, so that was the theorem. So if we go quickly through them again, theorems 1 and 2 deal with the convergence of this algorithm and the fact that it actually minimizes the proposed energy. Then theorem 3 says you can store exponentially many patterns in terms of the dimension of your space. And theorems 4 and 5 say that this update rule will converge exponentially fast after one step, if you believe that, and the retrieval error will also go down exponentially fast with the number of update steps that you do. Okay, that sounds pretty good, but we've heard it, it's very dependent on how well separated these patterns are. And it turns out that, at least in transformers, they aren't always well separated, and that might be on purpose. Remember, the states here, the patterns aren't pre-stored like in a classic Hopfield network, but the patterns, if you interpret an attention mechanism as this, are also generated by the network itself. So the pattern matrix that you retrieve from and the query are generated by the attention mechanism in this case. As I said, this is applicable to many more domains than just this, but yeah. So there's another slight modification that you have to do to make this actually equivalent to an attention mechanism, and that is you'll have to recast the value, because usually what you'll do is you have some sort of input and then you make queries, keys, and values from that using different heads. The only thing to make it formally equivalent is you have to make the values generated from the keys. So the keys give rise to the values, as you can see right here, that you first multiply with the key matrix and then with the value matrix. I think that's, that I doubt that this will change anything. The only way that could really change anything is if this matrix here would be super low rank, like collapse the space of into like very few dimensions, which the value matrix wouldn't do. So, but just letting you know that the technical equality requires this slight modification. Okay, now we said that it might not, be that this is always super well separated and you retrieve a single pattern. And that's what they research here in a pre-trained BERT model. So they take a pre-trained BERT model from, I guess, from Hugging Face, and they just run a data set through it. And what they do is, so for each query, for each attention head, because you have multiple ones of these attention heads, right? In each layer. So in each layer, you have multiple ones of these heads. For each head, they look at, over the course of the whole data set, how do these softmax distributions look like? So when you believe that this is a Hopfield network, and you believe that this converges in one step, then if the patterns are well separated, what we would expect is a distribution, as we said, like this. Okay, there would be one dominant pattern that you retrieve. That's what you want to retrieve. That's what comes out. But bang, you retrieve that accurate pattern. Anything else would mean that the Hopfield network sort of failed, right? It wouldn't give you back one particular pattern. So they have I think it's a pretty smart experiment. They look how many bars do we need to add? How many of these bars in the softmax distribution do we need to add to reach 90%? Right? So it depends a bit on the temperature of the softmax, which is hard-coded in a tension mechanism. PdB is 1 this squared over d. So they say, how many do we need to add to get to 0.9, to 90% of the mass of this distribution? And if this is the Hopfield network where you retrieve one pattern, then 1 will be enough, right? 1 of these bars will probably be, I don't know, like 99%, okay? But there are other cases. Imagine the case where the patterns and the query you retrieve, the spheres that it gives rise to are all like overlapping, okay? So what that will do is it won't converge to any particular pattern, but the attractor space in this kind. So you can imagine if you have two spheres that are apart from each other, the update rule converges either. So if it's closer to here, it converge here. If it's closer to here, it'll converge here. But if they are overlapping like this, the energy landscape will actually make it such that it will neither, if it starts somewhere, it will neither converge to here nor to here. It will actually converge to somewhere in the middle, okay, into the mean of the stored patterns. And if we take that to the extreme, what could be is, it could be that the softmax distribution looks completely uniform, okay, which would basically mean that, you know, I don't care where my information comes from, just average. And this has its applications. So if you, for example, want to make a sentiment classifier, very cheap way to do that is to simply take pre-trained word embeddings like glove or word2vec, you know, assign each word a word embedding and then just average the word embeddings, okay? And you count on the fact if there are a lot of kind of negative words in there like bad, sad, angry, the word embedding kind of will, you know, reflect that, and the average word embedding will point more into the bad direction. And if there's a lot of happy words, the average will point into the happy direction, okay? So there are applications of averaging information, not caring particularly where it comes from. And in that case, what we'd expect is that this number, and we'll call that, so we'll call that the number k. In this case, it equals 1. But in this case, k equals, I guess, n, the number of inputs, okay? Because we need, well, not maybe n, but, you know, approximately, we need almost all of them to reach the 90%, okay? And there is an in-between, and these are called these meta-stable states, where, and the in-between is something like you'd have a couple of patterns here, a couple here, and a couple maybe here. It's almost like a clustering, like, and these overlap, and these overlap, and these overlap, but they don't overlap with each other, which means that if you start somewhere here, you would converge to the mean, but not to the mean of all the patterns, but just to the mean of these patterns, and here, here, and here, here. So this is like a clustering in latent space, right? So you can interpret these Hopfield update rules as somehow, you know, not going to a particular pattern, but going to sort of a cluster. And this is if you ask something like, hey, is there any adjective around, right? And all of these patterns, they kind of overlap in that space, in that query space of adjective, they overlap. And therefore the update rule would converge to sort of the mean, which would basically say, yes, there is an adjective here, right? And the information would not be routed, so that the distribution, if we start here, right, and we converge to this, the distribution would look something like small, 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 and then you'd have a couple of large ones, right? You'd have like maybe 2 or 3 or 4 of large ones, and these would exactly correspond to the patterns here. So the information will be routed from all of those in that cluster to this particular node that asked the query. Okay, these are what's called these metastable states, and what they do is they calculate over the entire data set this number k, and here they show you the distribution. So in these plots, what you'll see is over the entire data set, k goes into that direction. So I guess let's go to tis here. This seems pretty easy. So K is in this direction, and this is simply the amount of like how, so in each, you let a data point run through it, you measure K for that particular layer 1. You see this is layer 1 head 4. Okay, this is one layer 1 attention head. And then you can see that the number K is distributed like this. Okay, so contrast this to this head right here, where it's a lot of weight on the number 1, or like very few numbers. Okay, so these blue ones would be, these are your typical, like when you retrieve one particular pattern. So this attention head, we can sort of conclude in this particular attention head, this is very specific. It looks at its input, it looks at its token, and it decides what information do I want, and it retrieves one particular thing from the other nodes. Okay, whereas here it's more like kind of an averaging. It's more like I want this kind of information, and on average, I don't even know what the sequence length is here. I guess it's maybe 512. So of the 512, the median, this number is always the median, and median, it collects information from 231 of them. Okay, so you can see that this corresponds, these green and orange ones correspond to these metastable states, where there's kind of an implicit clustering done in the space of attention, whereas the blue ones, they correspond to attention heads that ask for particular information, retrieve one particular, maybe few patterns, and happy with that. And the red ones here, you can see that they often just average. They just, you know, because K is so high, it means that I need all of these bars to get to the 90%, or I need almost all of them, which basically means it's a uniform distribution, right? So it's like, I don't care where information comes from, just average, whatever, average. I just want the average in some particular space. And as we said, that also has its uses. Interesting how this translate through. So this here is, as we go down the BERT model, on the bottom you have layer 1, you see there are a lot of these averaging operations going on. So a lot of the heads are simply doing averaging. And as you go up the layers, the heads get more and more specific in the types of information they seek. But then again, in the last layers, interestingly, you get into a lot of these meta-stable states again, which I guess, again, interpret this as you want. I'm going to leave this up to you, but it sort of says like here you want kind of general patterns at the bottom, and then the middle layers are kind of the logical workhorses. So you look for very specific things in the input. This is, I guess this is where the thinking happens. So this is sort of pre-processing. I'm just making stuff up here, by the way. This must be in no way true. This is maybe thinking, and this here, this might already be output again, because, you know, after that you have language modeling or classification. So this might already be like aggregating types of information. This is how I sort of interpret it. Okay. Yeah, so these experiments are pretty interesting, and here these are the last experiments for this paper. They do an interesting experiment where they actually replace the attention heads by simply an average mechanism, and later they actually replace them by Gaussians, but in this case they simply average, and they show that, look, if I replace layer 1 with just averaging, the perplexity doesn't rise that much, right? So it's pretty good, even if I replace an entire layer here with averaging. The perplexity goes more up, and you can see the correspondence. If you remember the previous plot, the correspondence is pretty one-to-one with how much blue and green heads there are, as in contrast to how much red and orange ones there are. So here you have lots of blue ones, and you can see that the error kind of goes up. And interestingly, here you have more metastable states at the end, but still the perplexity goes up more. So I guess you can only really replace the red ones with the averaging. So this is always averaging in one particular layer. And they go into more detail here where they say, look, this is layer 6 and this is layer 12. So this is one particular attention head from layer 6 and layer 12. And the updates, don't be confused, it goes in this direction. Okay, I was confused at first. And you can see right here, this number k, at first, you know, it's kind of spread out, but then it pretty quickly converges to a very small number. And there is this kind of point right here. I don't know if the learning rates decrease. I don't think so. I think that's just kind of a phase transition right here. This is the blue line, by the way, the blue training line. A phase transition where all of a sudden these attention heads, they somehow decide, okay, this is the thing I want to specialize in. This is the type of task I want, like a subtask of linguistic subtask I want to specialize in, and then they concentrate on one particular pattern per input. So they are really specializing. Whereas in the last layer, you see here that even during training, they are sort of continuously learning. So first, they also do this averaging, then they go into this metastable region, right? This is this metastable region. K isn't 1, but also K isn't a very high number. So they continuously learn. And it's even indicative of this training might not be done here, first of all. And second of all, it would be really interesting to see how this works out with, you know, sizes of transformers, and like especially these huge transformers. Just the fact that they can keep learning the more we train them might be, you know, be interpreted in the light of what kind of states they converge to, and the fact that their attention heads, I don't know, how does this go on? Do they stay in the metastable states because it makes sense to have metastable states? As I said, it makes sense to kind of cluster things. Or are they simply, is there simply an intermediate step? And if you go really far down, they would actually also converge to the k equals 1, where they really specialize. Or maybe do we need more attention heads for this? I don't know. It's just, I think this is just the beginning of kind of research in this direction. I think just this kind of number k, how it's made is pretty simple, and apparently it's pretty revealing. So, you know, that's pretty cool. So that was the paper and its experiments. It's a pretty sizable paper, as I said. Even the paper itself is 10 pages, and then there is this immune repertoire classification, which I will like spend 1 minute looking at it. So you have these set classifications. So for each human, you obtain a set of immune receptors, and you simply obtain one label, whether that human is immune to a particular disease or not. And your task is and then a different human has a different set. You have no idea which one of these things is responsible for it being, for the human being immune or not. In fact, there is you can't even decide based on these. You can only decide based on like subsequences of these, and they might be in combination with each other. So there might not be a single one responsible, but like a combination. But you don't have labels for the individual ones, and you have different ones per human, and they are different length. All of this is just a giant task, and you have many of them. You have tens of thousands per human, right? So they build a system here where first they do these 1D convolutions to process the inside sequences, and then they do this Hopfield attention mechanism with learned queries over these things, and then they train on the output label. And surprisingly, that actually works, even with tens of thousands of inside sequences and only one label for all of them. And so they achieve, I guess, favorable results compared to other baselines on this task using these Hopfield network, which is pretty interesting, but I'll let you look at that paper yourself. So I hope this somehow made it a bit clear what happens here. And it would actually be pretty interesting if we to see what happens if we just do maybe 2 rounds of these updates. Is this even desirable, right? Is it desirable to run this to convergence? Is there something good about not running it to convergence, or does it actually not matter because it actually does converge in one step? I don't know, but have a look at the code. It's pretty cool, and I hope you enjoyed this video. I'm sure you have many open questions, as do I. Don't hesitate to ask me in the comments, or join our Discord. As I said, there are lots of helpful people on our Discord, and I'll see you next time. Bye bye.